Okay, this video is about areas and lengths in polar coordinates. And so if we recall the area of the sector of a circle, it is equal to 1/2 r squared theta, where r, if this is the sector of a central circle, and this is the arc, the radius r, and this is the angle theta, the area of this sector right here is equal to 1/2 r squared theta. Okay, it can be shown that the area of a polar region r, such as this, between angles A and B, even though it's not the area of a sector, but it's some crazy shape or some arc, not a nice arc, is defined to be the integral from A to B of 1/2 f of theta squared, where f of theta, the function of theta, is r. R is a function of theta. So more typically we write it as A is equal to the integral from A to B of 1/2 r squared d theta. So we'll be using that to calculate areas of using polar coordinates when we have things in polar graphs. So example 1 says find the area enclosed by one loop of the 4-leafed rows. R is the cosine of 2 theta. So before we do that, let's get an idea of what this guy looks like. And a nice way to do that would be to do the fast sketching that we sort of looked at in the last video, where we want to graph this. So if we consider this y is equal to the cosine of 2x, and let's graph this. The period 2 pi divided by b is pi, so that means what's happening here is if we take pi divided by 4 to get the major points, we get pi over 4, pi over 2, pi, 3 pi over 4, and pi. Okay, so cosine starts high, so it's up here at 1, and then it's middle, and then it's low, and then it's middle, and then it's high. So this is our cosine graph. Okay, so we can use this information to sketch our polar graph. And remember, here's our polar coordinate, and so I'm not drawing all the circles, but you know the radius goes out with all those circles, and this is the angle 0, and this is pi over 2, and 3 pi over 2, like this. Okay, so we can see that when the angle is at 0, r is 1. So if we're at 0, r is out here at 1. Okay. And then when the angle is at pi over 4, it's at 0. So when we move here to pi over 4, we've made it here to 0. So it goes like this is the first little movement that we have on our graph. So then from pi over 4, we go to pi over 2. So at pi over 2, we're at -1. So when we get to pi over 2 up here, instead of going up 1, we go down 1. So it looks like this. So this is 1 unit. And then when we get to 3 pi over 4, we're at 0 again. It's like that. And then when we get to pi, we're up here at 1 again. So at pi, it has us going over here to 1. And then if we continue another period, we'd end up going here. And then it's going to have us go up, and then down, and then up. This is what this 4-leaf rows basically looks like. I only went through 0 through pi, so I didn't graph the whole thing. We could go through 2 pi and it would complete it. But basically, this is what it looks like, and we want to find the area enclosed by one loop. So one of these petals is what we're looking at. So what I'm going to choose to do is to take the area of half of a petal and multiply it by 2 because it's symmetric. The only reason mine doesn't look symmetric is because I sketched it and I'm not a good sketcher. So what we have here is the area is equal to the integral from A to B, where A and B are angles. So this is angle 0, we're at 0, and then when we go to pi over, no, we're at 0, we were at 1, and then when we go to pi over 4, we're at 0, right? And so then from pi over 4 to pi over 2, we could get that. I shaded the one that was from pi over 4 to pi over 2. This is the part that I was looking at. I could have done 0 to pi over 4, but I'm going to do it this way. So we want to find the area of one of these. So since I only chose to do half, I'm going to multiply what I get by 2. Now, it's possible that this will be negative, so I'll take the absolute value of what I get because this is below the x-axis. We'll see what we get here. So we go from pi over 4 to pi over 2, 1/2 r squared, so r is the cosine of 2 theta squared d theta. All right, so this, since I'm doubling it to get the area, 2 times 1/2 is 1, so that took care of that. From pi over 4 to pi over 2, the cosine squared of 2 theta d theta. Now, I'm going to have to use identity. This is a very nice identity when you just have sine or cosine by itself. Cosine squared of x is equal to 1/2 times 1 plus the cosine of 2x. And the sine squared of x is equal to 1/2 times 1 minus the cosine of 2x. These are handy identities when you have to integrate just a cosine squared by itself or a sine squared by itself. So in this case, I want to rewrite this as 1/2 times 1 plus the cosine of 2x, but my x is 2 theta, so that's going to be 4 theta. So this is what I'm integrating now, pi over 4, pi over 2. Okay, so this becomes 1/2 plus 1/2 cosine of 4 theta d theta. All right. Pi over 4, pi over 2. Okay, so when I integrate this, I get 1/2 theta plus 1/2. Okay, the cosine of 4 theta, you can use a substitution where u is 1/4 and then make the adjustment. Or if you've done this enough, you can say, okay, what do I integrate to get what's the derivative that gives me cosine? It's sine, so it's going to be sine of 4 pi. But I have to make the adjustment, divide by 4. And if I'm not sure, I can just take the derivative of what I just integrated. The derivative of sine is cosine of 4 pi times 4, because of chain rule, that would get rid of that, and I get back. So I integrated that, okay. Now I want to evaluate this from pi over 4 to pi over 2. I'm doing this a different way than I did the first time I did it. So I should get the same exact answer. So we'll see, it'll be interesting to see how this goes, if I make a mistake or not. So here we go. This is 1/2 pi, so it's 1/2 pi over 2 plus 1/8 the sine of 4 times pi over 2 is the sine of 2 pi minus 1/2 pi over 4 plus 1/8 the sine of 4 times pi over 4 pi. Okay, the sine of 2 pi, this is a big 0. This sine of pi is a 0. So I'm left with pi over 4 minus pi over 8. I can get a common denominator of 8, and that's 2 pi minus pi over 8, which gives me pi over 8, which is the area in one loop. This is what the area of one loop is. And that's what I got when I did it an alternate way. So that's good, check. All right, example 2. Find the area of the shaded region. So it may not be clear because of the copy, but this is the shaded region that we're after. So if we want to find this area of the shaded region, let's look at what angles this goes from. This goes from here to here. All right. So I'm going to say this is negative pi over 2 to pi over 2. That's the angles I'm integrating through. R is defined to be this, so this is pretty straightforward. The area is going to be the integral from negative pi over 2 to pi over 2, 1/2 r 4 plus 3 sine of theta squared d theta. All right, I'm going to put the 1/2 in front. Negative pi over 2 to pi over 2. I'm going to square this term. That's going to be 16 plus 24 sine of theta plus 9 sine squared of theta d theta. Now here I have this single sine squared. I'm going to use this same identity again to help me out. So this is going to be 1/2 integrate negative pi over 2 to pi over 2, 16 plus 24, the sine of theta plus 9 times 1/2 times 1 minus the cosine of 2 theta. And this is with respect to d theta. Okay, let's integrate this guy. The 1/2 we'll leave you out here. This is 16 theta. When I integrate sine of theta, negative 24 cosine of theta is what I get. Okay, I've got 9 times 1/2, which is 9/2 times 1. Okay, 9/2, if I'm integrating him, that's going to be theta. And then I have negative 9/2 cosine of 2 theta. So if I'm going to integrate this, that's going to give me the sine of 2 theta divided by 2. So 1/2 the sine of 2 theta. And all of this is from negative pi over 2 to pi over 2. All right, let's plug in some stuff. This is going to be 1/2 times 16 times pi over 2 is pi over 8. Cosine of pi over 2 is 0. That's a 0. 9/2 times pi over 2 is 9 over 4 pi, minus 9/4 sine of pi is another 0. Minus, when we put in negative pi over 2, we get 16 times negative pi over 2, negative, did I write pi over 8? That's a mistake. This was supposed to be 16 times pi over 2, which is 8 pi. Sorry about that. Okay. Minus 16 times negative pi over 2 is negative 8 pi. Cosine of negative pi over 2 is 0, so that's a 0. 9/2 times negative pi over 2. Negative pi over 2. Sine of negative pi is 0 plus a 0. All right, let's see what we got. We got 1/2 times 8 pi plus 9 over 4 pi plus 8 pi plus 9 over 4 pi. Let's see, that's 1/2. 16 pi plus 18 over 4 pi. That's 1/2. That's 64 pi plus 18 pi over 4. Let's see, 64 plus 18 is 82 over 8 pi. And I can divide each of those by 2. This is 41 over 4 pi. That is the area of that region. Okay, couple more examples. Example 3. Sketch this curve and find the area it encloses. So, if we sketch this curve, I'm going to do the fast sketch, and then using Cartesian, and then I'm going to y is equal to 3 plus 2 cosine of theta. Okay. I think I'm missing a little r equals. And let's see what this would do in polar to figure out what region we're sketching, what area we're trying to figure out. So if I sketch this curve, 2 cosine of theta. I'll deal with the vertical shift in a second. The period's 2 pi. So this is pi over 2 pi. 3 pi over 2, 2 pi. It's got an amplitude of 2. Okay. Cosine starts high, middle, low, middle, high, high, middle, low, middle, high. Now this is a vertical shift. So normally this would be 0, but it's you add 2 to everything. This is 2, 3, 4. Nope. I went up 3, not 2. I add 3 to everything. So this will be 3, 4, 5, 2, 1. And 1 below that is my x-axis. So here's my x-axis. What does this line become? It just becomes like the midline through the curve. So this is just 3. So this entire thing is above the x-axis there. Okay, let's convert that to a polar graph. If we convert this to a polar graph, where this is pi, this is 0, this is 3 pi over 2, this is pi over 2, we can see that when theta is 0, r is 5. So we're out here at 1, 2, 3, 4, 5. Okay. And then when theta is pi over 2, we're at 3. So we're up here at 3. And then when we're at pi, we're just over here at 1. And then when we're at 3 pi over 2, we're back at 3. So we're out 3. 1, 2, 3. And then at 2 pi, we're back at 5. So what this guy's going to do is kind of go up here, around here, around here, around here. And this is another one of those cardioid shapes. So if we want the area enclosed by the entire region, then we'll just go through one cycle, one loop. Let's integrate here from 0 all the way around to 2 pi. Okay, and then that's going to equal to 1/2, which I'm going to put out here, r squared, 3 plus 2 cosine of theta squared d theta. So this is going to be 1/2, 0 to 2 pi, 9 plus 12 cosine of theta plus 4 cosine squared of theta d theta. All right, here we have another one of these cosine squareds. I'm going to use that same identity. So we have this is the 1/2 here. We're integrating from 0 to 2 pi, 9 plus 12 cosine of theta, 4 times 1/2 times 1 plus the cosine of 2 theta d theta. Okay, let's integrate. This is going to be 1/2 9 theta plus 12 sine theta. Oop, there's a plus. Plus 2 times 1 plus 2 theta. Plus, I've got a 2 here in front of this distributes. I have a 2 here. 4 over 2 is 2. But when I integrate, and this is the 2 theta, I'm going to be dividing by 2, which is going to cancel to be a 1. So I end up with the sine of 2 theta. And this is evaluated between 0 and 2 pi. All right. We have 1/2. 9 times 2 pi is 18 pi. The sine of 2 pi is 0. 2 times 2 pi is 4 pi plus 4 pi. The sine of 4 pi is 0. And then we have minus 0, sine of 0 is 0, 2 times 0 is 0. This is a big 0. Okay. What do we have here? We have 18, 19, 20, 21, 22 pi divided by 2, or 11 pi. That is the area of this cardioid right here. Okay, last example, and this is to do with the length of a curve. So the length of a curve, it can be shown that the length of a curve with the polar equation is the integral from a to b, where a and b are angles, of the square root of r squared plus dr d theta squared d theta. the proof for these formulas is found in the text, and so you can see exactly how these came to be. Example 4, find the exact length of the polar curve where r is equal to 2 cosine of theta from 0 to pi. So, we have our r. We need dr d theta. Dr d theta is equal to 2, derivative of cosine is negative sine. So this is what dr d theta is, negative 2 sine theta. So the length is equal to the integral from 0 to pi of the square root of r squared. Well, r is 2 cosine of theta squared plus dr d theta squared, negative 2 sine of theta squared d theta. All right, here we go. This is 0 to pi, the square root of 4 cosine squared theta. Negative 2 times negative 2 is 4 sine squared theta d theta. I can factor out a 4. And hopefully you remember that this is the Pythagorean identity. Sine squared plus cosine squared, or cosine squared plus sine squared, is 1. So this is really 4 times 1. So we're really looking at the square root of 4, which is 2. Let's integrate. This is 2 theta, evaluated from 0 to pi. This is going to be 2 times pi minus 2 times 0, or 2 pi. That is the area of this curve. Now let's just see what's going on here, and I think that once you see this, it will give you a little bit more faith in the formulas where they come from. If we were to graph this, let's graph this guy. Here's a little quick sketch. Think of y is 2 cosine of x. If we have y equals 2 cosine of x, we're going up 2, down 2. It starts high, middle, low, middle, high. And this is 2 pi. This is 3 pi over 2, and this is pi, and this is pi over 2. We can get a quick sketch of the polar coordinates, which says at 0, at angle 0, we're out here at 2. All right. And then at pi over 2, we are at 0. Okay. And then at pi, we're at negative 2. So if we're out here at pi, we're at negative 2, then we're back here. What this is doing is going here, and then it's going here. And then once we get back to 3 pi over 2, we're here. And then at 2 pi, we're at 2 again. So this is a couple of cycles of this, of a circle. So this is a circle centered at 1, 0 with a radius of 1. What did we just do in this problem? Well, we found the arc length. Well, the arc length of this figure is the circumference of this circle, and the circumference is equal to 2 pi r, but r is 1 in this case, so the circumference is 2 pi. This is exactly what we just calculated using this formula. So if we can do it for a simple example like this, it's going to also work for more complicated curves.